Now let's look at this problem here where we want to find again the derivative, the first derivative and also the second derivative and the tangent line at x equals 1. So we started with this first line, f of x equals 7 times e to the 2x plus 8 over cube root of x. We want to take this second part and write it as x to the negative 1/3. And so then when we take the derivative, we first start by using the sum rule and say that we're taking the derivative of each piece. Okay, and then I can use the constant multiple rule, which brings that out front. And this part right here you want to think of as e to the u, where u is the 2x. Now when you think of it that way, then in fact we know how to do this. So again, the 7 pulls out front. The derivative of e to the u is e to the u times the derivative of the u. And we know how to do this, the polynomial function. So it's negative 1/3 times 8 is negative 8/3 times x, and then we got to work on the power here. Negative 1/3, you subtract 1 from it. Negative 1/3 minus 1 is negative 1/3 minus 3/3. That's negative 4/3. Okay. Now we substitute back in the 2x. Some of this you might be able to do in your head, but I'm going to go ahead and show you all the steps. This I can write as x to the positive 4/3 if I move it down to the denominator. Okay, the derivative of 2x is just 2. So now we actually have the derivative. 4/3 is x to the x to the 1 and 1/3. So there's the fourth. It's just an x and then a third root of x. Okay, and then finally, one final step. I can put the 2 and the 7 together, and they multiply together to get 14. And then the u is this 2x, so I can put it back in place here. Now you might have been able to do this substitution in your head. In fact, likely you could. As you get a little bit more practice at this, you can start doing a few things in your head. You absolutely cannot skip any steps, but you can do a few things in your head perhaps. So for example, we could have just said, well, the derivative of 7e to the 2x is the 7 times e to the 2x times the derivative of the 2x, which is 2, and got this to be 14e to the 2x. We might have been able to do that part just completely in our head, but we were really doing a substitution. We were saying this is e to some power, so the derivative is e to that power times the derivative of the power. That's how the exponential rule works in conjunction with the chain rule. Okay. Now we have the derivative there. Actually, I'm going to think back now and think of the derivative in this form. As 14 e to the 2x, and then I'm going to think of it like we had it here for the other term, but when I get ready to do the second derivative. Let me see if I can do a little bit more in my head this time. Okay, again, the derivative of 14 times e to the power is 14 times e to the power times the derivative of the power. The derivative of the power is 2, so that's going to turn this 14 into 28. Similar steps as last time, just did them in my head this time. Now we take the negative 4 times the negative, here 8 thirds is positive. 3 times 3 is 9 in the denominator. 4 times 8 is 32 in the numerator. And you subtract 1 from the power, we're adding a negative 3 thirds, so this is negative 7 thirds. So there is the formula for the derivative. We were able to work it out completely in our head. Okay, and this part here with the fraction, we can, with the fraction exponent, we're going to rework that. It's going to go to the denominator. It's very similar to this one here. In the denominator. Let's see, it's going to be 7 thirds in the denominator. In mixed number form, 7 thirds is 2 and 1 third. The 1 third is the cube root, and the 2 needs to go on the power of x there, and that's going to take the place of that part. And so there is a nice formula for the second derivative. Okay, and now we want the tangent line. Okay, so to do the tangent line, we first need to find the point of tangency, and that is to take the original function and we wanted to evaluate that, and we've been doing this at 1, so let's find the tangent line at 1. So we take everywhere there's an x and put a 1 in there. One thing nice about putting a 1 in is some things are simpler. So this is 7e squared. So, okay, let's take this. 2 times 1 is 2. So that's 7e squared. Cube root of 1 is 1. 8 divided by 1 is just 8. Okay, so there's the x, the y value that goes with an x of 1. And any one of these I could use. Let's say we use this one for the derivative. And we put in 1 here. And we put in 1 in place of the x's here and here. Well, what does that turn out to be? Well, this is 14e squared. Okay, well, it is minus 8 thirds. So that's the slope. So what's the formula for the equation of the tangent line? T of x, y equals, well, first of all you have the slope, which is this number here. And then you have x minus the x coordinate of the tangent point, which is point of tangency, which is 1, plus the y coordinate of the point of tangency, which is f of 1, this number right there. And so there's your equation of your tangent line. Okay, so let's graph those and take a look at the graphs and make sure everything seems to look right on the graphs for us. So let's start by graphing the original function. Y equals 7 times e to the power 2x. Notice I put the 2x in parentheses. Plus 8 divided by the cube root of x. Now to do the cube root of x on the calculator, I probably want to do x to the power parentheses 1/3. Be sure you put a parentheses around the power. It's actually optional in this case because it will do exponents before it divides, but let's go ahead and put a parentheses around the whole denominator too. It's a good habit to get into. So there's the original function. Notice some interesting things here. It's undefined when x is 0. Okay. But it should be defined everywhere else. I'm just not seeing the points over here. So let's take a look and see. They get pretty big here pretty fast. So I need to go up at least into the, well, to see the point of tangency, it's going to need to be about 60 almost. So I need to go up pretty high. Let's go up a couple hundred maybe. And look at that. So let's change the grid range. So this grid range thing is a little tricky. Sometimes you have to experiment a little bit. There we go. We can see it a little better there. Okay. So that's our original function. Okay. Now the derivative is supposed to be y equals 14 e to the power parentheses 2x minus 8 divided by parentheses. Well, let's do our final version. 3 times x to the power 1/3. Close the 1/3, close the denominator, and there's the derivative, which we'll do that in red. Okay. And then we can have the second derivative, y equals 28 e to the power 2x. 2x has got to be in parentheses. Plus 32 divided by parentheses 9x squared times x to the 1/3. That 1/3 needs to be in parentheses, and the whole denominator needs to be in parentheses. Okay, and that one, let's see, we've usually been using green, I think, for the second derivative. And the tangent line, y equals, let's see what y equals there. What does y equal? Okay, I'm looking at my other picture of it there. Parentheses 14 e to the power 2 minus 8/3, close parentheses, that's our coefficient, that's our slope. Then you got parentheses x minus 1 plus, now we got our y-coordinate of our y-intercept, 7 e to the power, or not y-intercept, the y-coordinate of the point of tangency. 7 times e squared plus 8, close parentheses, 8. And this should go through the graph at 1 and be tangent. So that looks pretty good, but we've got a lot of dead space here, and all we're really seeing is a lot of asymptote going on here. So let's zoom in a little bit from the sides and maybe a little bit from the bottom. Change our grid range just a bit. So maybe negative 3 to 3, negative 4 to 4. How about negative 4 to 4 on the x's? We can come up quite a bit. Let's just go from, say, negative 50 on the bottom to 200 on the top, maybe. See what that looks like. Let's go a little. That's better. That's a lot better view. Let's go a little bit further down. Let's see. We'll go negative 100 and then maybe 250. There we go. That's not bad. Let's get this tangent line a different color. Then let's see. We'll go. Actually, let's go with green for the tangent line, and we'll go with purple for the second derivative. So the original function is blue, and then the derivative is red, and the tangent line is green, and the purple is the second derivative. Okay, so let's see if we can put our labels where they go. F of x is the blue function. Let's put it right there. And let's put the label for the derivative. It's going to be by the red one somewhere. How about right there? Well, how about right here? And then the f double prime, we need to put it by the purple one somewhere like that. And the label for the tangent line, we'll just place it over here. Now let's take a look at this and make sure this makes sense from the shape of the graphs. So the original function we notice is decreasing here, so the derivative is down the negatives. It's decreasing here, so the derivative is down the negatives. Where the derivative crosses the x-axis right here, that's right above that is where the original function has a minimum. And then beyond that, the derivative is positive because this function is increasing. Now let's see, it looks like the derivative on this part here where x is positive is always increasing. So that says that the original function is, or the second derivative is positive, which it is, and the original function is concave up, which it is. So that makes sense. And then over here we see that the original function is decreasing, so its derivative is negative. The original function is concave down, so the derivative is decreasing, and the second derivative is negative. So that makes sense. They all seem to be leveling out to asymptotes here. So this looks like they're all coming out to a horizontal asymptote. And if you go down this way, it looks like they all have vertical asymptotes of the y-axis there as well. Everything's undefined when x is 0, and certainly that's no surprise looking at the formula, because the formula, the original formula, if you remember, had a cube root of x in the denominator. So anytime you got an x in the denominator, or just an x or x to a power, 0 is going to make you divide by 0. So that's undefined. So that's going to give us notice that gives us a vertical asymptote on everything here. The tangent line seems to work. It looks like it should be crossing at 1, comma, whatever here, with a point of tangency, and it is going along there. So the graph characteristics seem to be panning out, so hopefully that means we didn't make any mistakes. Now, of course, we could check our answers. Okay, don't forget how we can check some of these answers. Let me show you how to check the first derivative. Okay, with your graphing calculator, just to remind you. Now we can always check any derivative problem this way. So we put the original in, 7 e to the power 2x plus 8 divided by cube root of x. There actually is a cube root of x if you look under math, 4, and cube root of x, x. There we go. That's the original. And so then under y2, you can set this up as math, number 8 is a numerical derivative. Taking the derivative with respect to x of y1 and you're evaluating at a variable x so that we get a whole formula. We get a whole function there. Now that's a symmetric difference quotient of the original, so it's an approximation of the derivative. The actual derivative is the formula we came up with. Hopefully it is, with no mistakes. 14 e to the 2x, and then minus 8 divided by parentheses 3x times the cube root of x and I think I've got all my parentheses where I need them. I don't like the way that looks, but it's 3x times, maybe I should back that up to make sure you're clear. Okay, now when I look at the table, what should I see? I should see y2 and y3 the same. Okay, they're considered, oh, that's y1 and y2. Okay, where's y2 and y3? Yeah, those are coming out about the same. Of course, they're a little different, and the digits that they're different, that's the approximation in y2. The real deal is over here in y3. Of course, that's rounded off too, but for many digits, they're all correct. So, it checks out. So remember, you can check any derivative formula this way with the TI-84 level calculator. Put your original function in y1, let y2 be the numerical derivative of y1. Make sure you got an x in here, not some number. And then y3 is the formula you come up with for the actual derivative. Check to make sure the tables for y2 and y3 are the same. So we could check that. In general, we could check our formulas like that, and then check that the tables do in fact match as well. Okay, so that gives us a nice little check. Okay, so I think that kind of knocks out that problem. And then why don't you go ahead and work on the next one and then come back and check it out in the next video. There's the problem for number 7.